Hello, folks. So, our next chapter talks about things like the Pythagorean theorem, which hopefully rings a bell, um, and try more about triangles. So, we've already talked about how triangles could be congruent to each other and how triangles could be similar to each other. But this next section talks more about lengths of triangles using the Pythagorean theorem. Hopefully, you remember that as a squared plus b squared equals c squared. But before we can do that, we need to talk a little bit about the algebra behind that. So the first thing is this weird word called a radical. You actually know what a radical is, whether or not you realize it. A radical is something as simple as this symbol here. You probably know that symbol as a square root symbol, and it is. But that's not the only type of radical that we have. We can have the cubed root of something. We can have the fourth root of something. We could have the fifth root or the sixth root or the seventh root or the eighth root of something. And you could have the 41st root of something, right? You can have any kind of root that you want. So the radical itself are these symbols. And then we'll talk about what they actually mean here in a little bit. Now, the idea is that we're going to be simplifying radicals. So let's backtrack to something that you're familiar with. When you learned about fractions in elementary school, we talked about how we can reduce those fractions, right? So if you got down to a final answer in a problem that was, let's say, 3 over 6, you would never leave your answer as 3 over 6, right? Because 3 over 6 can simplify, can reduce to something else. 3 over 6 reduces to 1/2. That's if you were leaving your answer as a fraction. Of course, we could have said 0.5 as well as a decimal. And it worked the other way too, right? Like if I had 20 over 5, you wouldn't leave your answer as 20 over 5. You would actually simplify it to be 4. So in the same way that we can simplify fractions, let's do another one. Let's do 6 over 18. Now, 6 over 18, we could say, ooh, both of those are even numbers, so let me reduce it again, and let's do 3 over 9. Oh, but then hopefully you go, okay, 3 over 9, both of those are divisible by 3, so that can further be reduced to 1/3. So in the same way that you can simplify fractions, we can simplify radicals. Now, before we do that, we need to discuss what the heck is a perfect square. Now, hopefully this term rings a bell for you. And I'm going to be very, very informal in my definition of a perfect square. Okay, you would not find this in the textbook. This is just probably what will mentally make sense to us. A perfect square, hopefully you think about a number like the number 16 or the number 9 or something like that. So perfect squares are the number we get when we multiply a number times itself. So let's do that. Let's multiply a bunch of numbers times itself. Now, instead of writing out like 1 times 1, a different way of writing that out is 1 squared, hence why we're going to get the perfect square. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared, 81, 10 squared, 100. Hopefully you are pretty savvy with this list. If you don't know your perfect squares 1 through 10, that's your first bit of homework tonight. The second chunk of numbers is important as well, but definitely 1 through 10. You have to know those by heart or else your test is going to take you forever. Okay, 11 squared is 121. 12 squared, 144. 13 squared, 169. 14 squared is 196. 15 squared, 225. 16 squared, 256. 17 squared, 289. 18 squared, 324. 19 squared, 361. And 20 squared is 400. Okay, so all of these numbers are square numbers. Now, not all of them, like 2 is not a square number, but 2 times 2 is a square number. So our final answers in this list, what I'm highlighting here in green, these are the square numbers, not the first numbers. We can multiply any number times itself, right? So if I can multiply any number times itself, then that number isn't really special. The special thing is what you get when you do that. Now, what is a square root? So a square root, again, extremely informally, we can say is the number when multiplied by itself, the number when multiplied by itself gives us a perfect square. The number when multiplied by itself gives us a perfect square. So like what numbers gave us the perfect square? So the perfect square of 9, the number 3 gave us that, right? Because 3 squared is 9. So then we could say 3 is the square root of 9. So inverse operations, let's think back to like the inverse of multiplication is division. The inverse of addition is subtraction. The inverse of squaring a number is taking its square root. Okay, so square roots are essentially the inverse, or another way of saying that is just the opposite of squaring a number. The opposite of squaring a number. Okay, so let's look for an example. 4 squared technically means 4 times 4, right? Which is 16. Therefore, we can go backwards. That must mean the square root of 16 is 4. So that's the relationship. That's how it works. Now, both of these in this case happen to be perfect squares, right? Because 4 is on this list of perfect squares. 16 is on this list of perfect squares. That doesn't always happen. That's just a coincidence. Now, not every number is a perfect square. Otherwise, there wouldn't be anything special about it. Only the numbers listed above are. That's kind of shortchanged it a bit. We'll say plus some others. Or even many others. Good golly, there are an infinite amount of square numbers. The point, though, is on this list above, we could keep going with the list, right? We could do 21 squared, 22 squared, 23 squared, etc. So only these numbers, but plus many others. So 2 and 3 and 5 and 6 and 7 and 8 and 9 and 10, nope, sorry, 9 is, and 10, 11 and 12 and 13 and 14, right? None of those are perfect squares, just the ones highlighted in green. Now, how can you figure out what a perfect square actually is? Well, visually speaking, what it literally means is that if I had that number of tiles, per se, square tiles, then I could make literally a perfect square. So like 1 is a perfect square because 1 square by itself makes a perfect square. Ta-da! 1 by 1, right? Now 2 is not a perfect square because if I put 2 square tiles next to each other, then I get a rectangle. 3 is not a perfect square because then I get this little Tetris looking piece. But 4 is a perfect square. When I put 4 square tiles lined up, I get a bigger square. 5 is not a perfect square. Again, you get like a Tetris piece. Hopefully y'all know what Tetris is. 6 is not, you get a rectangle. 7 is not, you get this weird looking thing. 8 is not, but 9 is a square number. And we can keep going. 10 is not. 11 is not. 12 doesn't make a square. 13 doesn't make a square. Neither does 14 or 15. but 16 does. And we could keep going and going and going. And the pattern essentially is to add one more row and column. So the next one we would add here, 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 here. And we would make our next square number, which would be 25. And then you could continue the pattern forever. So moving forward, if I can't have a perfect square, so let's take the number 12, for instance. If I take the square root of 12, if you type that into your calculator, so to hit in your calculator, I'm pretty sure you know where this is, but just in case, you're going to hit the second, and then it's the x squared button, which will, ideally, it will generate that square root button. So if you take the square root of 12, you're going to get a decimal. Particularly, you're going to get 3.464101615, da 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 da. And you can't write that whole answer because that number actually goes on forever. So you could do two things. Your first choice is just a calculator approximation. Calculator approximation, where you essentially will end up just rounding to the nearest tenth, hundredth, whole number, whatever. The second option is to simplify the radical. This one is nice because we don't shortchange our number. We're not rounding it. Simplifying it will give us the exact answer. So how does that work? I've broken it down in steps for you here. So if you follow my list of steps every single time, you won't mess it up. Okay, so let's do the square root of 50. The goal is to find the largest square number that we can divide into the radical number. And I should also add, we can divide anything, but I should say that the largest square number that we can divide into the radical number, this word here is important, evenly. So step one, if you don't automatically know a square number that can go into 50, then just write out all of its factors. So it's basically the pairs of the numbers that multiply to get 50, right? So let's start with 1. So we've got 1 and 50. 2 is a factor. It goes into 50 25 times. 3 is not a factor of 50. 4 doesn't go into 50 evenly, but 5 does. 5 goes into 50 10 times. 6 is not a factor. 7 is not a factor. 8, if you divided that, would not be a factor. 9 would not be a factor. 10 is a factor, but it's already on the list. And then any numbers above 10 we would have already gotten by doing the factors that way. So once you get to that point, you can stop. So here's your list of square numbers. Now, step 2 is determine what is the largest square number. Largest square number that is a factor. That word largest is super important. So if I look at my list, let me first cross off everything that's not square. Okay, 1 is a square number, so I'm going to leave it there. 2 is not. 5 is not. 50 is not. 25 is. It's on the list up here, right? So 25 is a square number. 10 is not. So the largest square number out of this list would be 25. Now, step 3 is to actually simplify. So we're going to simplify the radical number using that square number times the remaining factor. So essentially what that means is if I have the square root of 50, we already said that 25 is a factor, so I could rewrite 50 to be the square root of 25 times the square root of 2, right? Because 25 times 2 gets me back to 50. Now, when I do this, step 4, this isn't, critical. I put the word circle here, but you could you could box it, whatever. You could just know whatever it is that you're doing. You're going to circle your square number, and then after circling, you're actually going to take the square root of it to remove it from inside the radical. Okay, so in that step prior to this, we had the square root of 25 times the square root of 2, but the square root of 25 is a square number, or 25 is a square number. The square root of 25 is just 5. So step 5 says leave any remaining factors on the inside of the radical. So the square root of 25 is 5, and then leave the square root of 2 alone. You can't do anything else with that. So simplifying radicals doesn't mean that you're going to get rid of all of your radicals. It just means the number on the inside of it should be a lot smaller. Step 6, check your answer using calculator approximations. So in your calculator, if you were to type in the square root of 50, we would get a decimal. It'd be, remember this symbol here, that little equal sign that looks like it got blown in the wind? That means just approximately. So anytime you round in math, we're going to use that approximation symbol. So the square root of 50, if you type that in your calculator, would be approximately 7.071, and then it keeps going on and on and on. Well, check that with your answer, with your simplified answer. 5 square roots of 2, if you type that into your calculator, will also give you about 7.071, and everything else matches up as well. So once you verified that those are the same things, then you know that your simplification was correct. So the square root of 50, anytime you see that, can be reduced to 5 square roots of 2. So let's do a few more examples. Simplify the following radicals.